Section 6A1 is families of functions. We're going to talk about functions. The specific families that we'll discuss will be in today's notes. There are 3 of them, and we'll talk about how we can transform them. A parent function. A parent function is the simplest form in a set of functions that form a family. So the parent function is basically the graph that hasn't been moved in any way, shape, or form, or stretched, compressed, which is something we'll get to in a little bit. It hasn't been changed. It's at its most basic form. If you change it or move it in any way, shape, or form, it's called a transformation. So everything that happens to that equation from its parent is called a transformation because it's different just a little bit. So this slide could be a little confusing, so focus on one color at a time. This is an absolute value graph. It's a V-shaped graph. The parent of a V-shaped graph is the blue one. It's centered at the origin, goes up on both sides. If I take that absolute value graph and I slide it to the right, it becomes the red one. Or I can take it and slide it up, at which point it's the blue, or the purple one, sorry. Or I can take it and slide it down and to the left, and it becomes the green one. You can move graphs all you want. And there are other things you can do to them as well. You can flip them, you can make them bigger, you can make them smaller. But this slide just shows you how you can take that parent function and slide it. There are 3 basic parent functions we're going to look at in the class. The first one, and you're very used to this one, is the linear parent function. That one's the one over here on the left. And the most basic form of a linear function is y equals x. The one in the middle is an absolute value. An absolute value function is centered at the origin, and on either side has a slope of 1. So you'll notice on the right it goes up 1 over 1, and on the left it goes up 1 over 1. And the last one, x squared, is called a quadratic. Every x squared equation is a quadratic. There are 3 types of transformations. We'll look at the first one today. That's a translation. A translation is a slide left, right, up, or down. The other 2 are reflections, stretches, and compressions, which will come in day 2 of section 6. A translation slides the parent graph, right or left, or up or down. Or it could do a combination of both, like we looked at a little bit earlier on that graph. So I want to give you a shortcut to the stuff you saw on the last screen. I'm going to use the words inside and outside, and I'll show you what they mean in a second. If it's inside, it's x, and it's opposite. If it's outside, it's y, and it's normal. And by inside and outside, I mean grouping symbols like absolute values or parentheses. Those are probably the most common ones that you're going to see. So if it's inside grouping symbols, it's done to the x and it's opposite from what you would expect. If it's outside, it's done to the y and it's normal. So the parent function that they give you in this problem is y equals the absolute value of x. So they're basically saying, tell me how this has moved from the parent function. So if you look at letter A, the change here is the +1, and that +1 is outside of absolute values. So it's going to be done to the y, and it's normal. So in the y direction, a +1 moves up 1. Letter B, that -5 is done inside. So that's going to be done to the x, and it's opposite from what you'd expect. In the x direction, like on a number line, a -5 leads you to believe it moves to the left, but it's opposite inside. This actually moves to the right 5. Letter C, the +6 inside is done to the x, and it's opposite. We think a plus moves to the right, but actually moves to the left 6. And then letter D, the -2 is done outside of the grouping symbols, which means it's done to y, and it's normal. A -2 moves it down 2. Pause the video for a second and do the you try it. Example 2, how are the functions y equals 2x and y equals 2x minus 3 related? How are their graphs related? So we're going to look first at the relation that they're giving us based on the equation. The difference between y equals 2x and y equals 2x minus 3 is the -3. And it is not inside any kind of grouping symbols, so it has to be outside. And a minus 3 outside actually moves it down 3. So to prove that, I'm going to graph both of these on the xy axis. I'm going to do y equals 2x first. That is a line that starts at the origin, goes up 2 and over 1, a couple of times until you can draw a line. And y equals 2x minus 3 is a line that starts at negative 3, goes up 2 over 1, a couple of times, so you can draw a line. So if you look, the only real difference between the red line and the blue line is that the blue line has slid down 3 units, which is what we expected based on the equations. I'm going to get rid of those lines and do the second part on the same graph. I just wanted to borrow it. Letter B, what is the graph of y equals 3x translated 2 units up? So you have two options for this. You can graph y equals 3x and move it, or you can get the equation. At this point, it's probably more comfortable for you to graph y equals 3x and then move it. Y equals 3x goes through the origin, goes up 3 and over 1. So if I want to move that 2 units up, I'm going to take every ordered pair, every point I put there, and move it up 2. Not moving it any other way, I'm just moving it up 2. So I'll draw this, although I'm not sure that's going to make sense. I'm going to move that one up 2, I'm going to move that one up 2, I'm going to move that one up 2. And so I end up with a line that looks very similar to the red line. It's only up further. And that's what a translation does. It doesn't change the general shape, it just slides it left, right, up, or down. Letter C, what is the graph and equation of y equals negative 2x translated 5 units down? You want to translate something 5 units down, all you do is tack a minus 5 on the end. Oh, it's a negative 2x. Hold on. Just throw a minus 5 on the end. That's what down means. So that's a graph that starts 5 units down, whose slope goes up 2 and to the left 1 because it's negative. Negative slopes go up and to the left. If you want to move something down, just tack a minus 5 on the end. If you wanted to move it up 5, you would have done a plus 5 at the end. Letter D, 4 units left. To the left has to be inside grouping symbols. And in order for us to be the left, even though we think it's a minus, it's a plus. So I know that inside grouping symbols, I need an x plus 4. Anything they gave you originally needs to be part of your equation. So they already had a y equals negative 2 there. So all you need to do is pretty that up, and by pretty up I mean distribute the negative 2. You get y equals negative 2x minus 8. And that's what you're going to graph. Negative 8 is where you start. It goes up 2 and to the left 1, and then connect it. Hopefully a little better than I did. So if you want to move anything left, one more time, I'll put this down here in case you didn't write it down. Left is inside, and it's plus. Right is inside, and it's minus. Up is outside, and it's plus. Down is outside, and it's minus. So again, these two are opposite, these two are normal. It's what you would expect. You're going to notice that in this set of view triads, those red squares, I'm not entirely sure why they're there. It's kind of like a a weird smartboard thing. In these, they took the parent function and just slide them. It's a lot easier for you, but the equations are not up there. I want to make sure that I include them for you. In letter E, x squared, 3 units to the right, subtracts 3 inside. So you're going to do x minus 3 inside and build everything else around it. In letter F, I went 2 units up, and that's a plus 2 on the end. Build everything else around it. So those are the 2 equations for the U-triads. All right, they want you to make a table of values after translating them. So you need to consider what value gets affected when you move things left, right, up, or down. So in letter A, they want to move it 2.5 units down. Down is done to the y values, and remember f of x is the same as y. If you want to move something 2.5 units down, that means I want to do f of x minus 2.5. So I'm essentially going to take all of those highlighted values and subtract 2.5. So if I had a 5, subtracting 2.5 is 2.5. If I had a 2, subtracting 2.5 is a negative 0.5. The negative 4 becomes a negative 6.5, and the 2 becomes a negative 0.5. So all I'm doing is subtracting 2.5 from each of them. Letter B, they want me to move it 5 units up. Again, up is in the y direction. So I'm going to highlight the y column, and my new column will be f of x plus 5. So each of those values, I'm going to add 5 to them. The 0 becomes a 5, the 3 becomes an 8, negative 5 becomes a 0, and 4 becomes a 9, because I'm adding 5 to each of them. Pause the video for a second and do the U-try it. Letter H, make a chart for f of x shown below, then chart the values for f of x plus 3 and graph them. X plus 3, that plus 3 that you see is going on inside, and a plus inside moves it left 3. So I'm actually going to make the original chart first. I have x's and I have f of x's. I'm going to pick each ordered pair from left to right, doesn't really matter. I'm going to do this one first. That ordered pair is a 1 for x and a 1, 2, 3, 4, 5, 6 for y. The second ordered pair is this one. X is 2, y is 5. This one, x is 3, y is 1. And this one, x is 6, y is negative 1. So if I take that and move it 3 units to the left, consider what's happening here. This orange one, 1, 2, 3, over is right there. This blue one, 1, 2, 3, is right there. The green one, 1, 2, 3, and the purple one. So you'll notice it has the same general shape. It just moves a little bit. The new ordered pairs of f of x plus 3 moves it to the left 3. So now it's not affecting the y values, it's affecting the x values. And it's going to take them and move them 3 units over. So what was at a positive 1 for x, and that was that purple point, is now at a negative 2. I'm subtracting 3. What was at 2, that green point originally, is now at a negative 1. Subtracting 3. What was at 3 is now at 0. And what was at 6 is now at 3. I didn't move it in the y direction this time. I moved it in the x direction. And by moving left, I'm subtracting values from x. Example 5. The graph on the left shows the projected altitude, f of x, of an airplane scheduled to leave at noon. So at noon. If the plane leaves 30 minutes early, what function represents this transformation? So I'm going to pause just for a second and consider the fact that if they're leaving at noon and now all of a sudden they're leaving 30 minutes early, that means that they're leaving at 11:30. That's before noon. So if you look at the graph on the left, I do want to point out the x-axis says hours after noon, so the 0 to 4 means like noon, 2 o'clock, 4 o'clock. So what I want to do is find a graph on the right that shows me leaving at 11:30. It cannot be the first one. That shows me leaving at 12:30. It cannot be the second one that shows me leaving at noon. It's actually this one. And the tricky part is they changed the scale on that. They slid that x-axis over. So the graph we are looking at is the graph all the way on the right. That's the one that shows us actually leaving before noon. Now, the other thing they want to know is what equation represents the graph that we're looking at. So again, we're trying to find the equation that would go for this. All we know is that the original equation is f of x, which is not overly helpful for most of you. We just have to kind of, at this point, determine what's going on. So remember that inside is where we want to take x movement. So even though the graph on the right looks like it's moving to the right, it's actually moving to the left. Remember, they slid that scale over. So instead of noon, we want it to be 11:30. Moving things to the left adds it inside parentheses. Left is adding, and we want to add 1/2 because it's a half of an hour, and that part's tricky as well. And remember, whatever was there has to stay there, so the f will stay as part of our function. Moving it to the left adds, and we wanted to add a half an hour.